Hello! I am here today to work this wave math practice page for Unit 7, our waves and sound unit. In number 1, we have a cork floating in water. It bobs up and down 4 times each second as small wave passes by. The speed of the wave is 0.4 meters per second. How far apart are the wave peaks? So this first number that they give us isn't really a number at all. I mean, it is a number, but it's kind of hidden in the words. It says that it bobs up and down 4 times each second. That is the frequency of the wave. And that is in hertz, Hz. The speed of the wave, it tells us, is 0.4 meters per second. And it asks how far apart are the wave peaks. That is wavelength. The equation that we're going to use for this one is the velocity or speed equals frequency times wavelength. And we just need to plug in our numbers. We will divide both sides by 4. And that will give us an answer of 0.1 meters. Number 2, a mechanical metronome makes 9 vibrations in 12 seconds. What is its frequency? The definition for frequency is waves or vibrations per second. And this question has vibrations in it. So that would be 9 vibrations in 12 seconds. So you just need to take 9 divided by 12. You'll get 0.75 hertz. Number 3, a very tall skyscraper swings to and fro in strong winds at a frequency of 0.15 hertz. What is the period of the skyscraper's oscillation? Our frequency is 0.15 hertz. The period is the inverse of the frequency. So we just take our frequency number and put it underneath that fraction. 1 divided by 0.15. That gives us a period of 6.7. Some people get confused about the period unit. It's a big T, and T is time. This unit, the 0.15 hertz, is equivalent to, in this case, it's more like oscillations, but you can think of this as being waves per second. So that would mean the 6.67 is the inverse of that. It would be seconds per wave. And you can just use seconds as your unit for period. I did not draw a box around this one. Number 4, a nurse counts 84 heartbeats in 1 minute. Find A, the period, and B, the frequency of the heartbeat. So the period is going to be the time per beat. Now, I didn't say seconds per beat, mainly because in this question you were given minutes. On the test, I probably won't give you anything with minutes or hours. I'll probably just stick with seconds. But in this problem, I did not. I gave you minutes. So you can either go ahead and say that that is 1 minute, and that's 84 beats in 1 minute, which would be 0.011 minutes per beat, which is not a really meaningful number, right? So if you wanted to multiply that by 60, you could, and you could make that more of a regular number of seconds. But I'm fine if you leave that in minutes. For B, the frequency Well, now that we took the time to find the period, it's easy to find the frequency. We're going to take 1 over 0.011, or you can just think about flipping this upside down. I'm sorry about all that noise. That is my dog. She is trying to make a nest out of a pillow, and it is I'm sorry, I'm shaking the camera now because she's making me laugh. Okay. Bailey, you're so noisy. Sorry. I'm sorry, I'm shaking the camera. Okay. So you can either take 1 divided by 0.00011, or you can say that's 84 beats per minute. That is the frequency. If you take 1 divided by 0.011, you're just going to get that answer. So you can either think of flipping this the other way around, or just saying, calculating it yourself and going, hey, look at that. That's the answer. 84 beats per minute. In number 5, if I could move the camera and show Bailey, I would, but I've got the camera. Oh, she's settled. Okay. Number 5, the crests of a long ocean wave are 24 meters apart, and in 45 seconds, 10 crests pass by. What is the speed of the wave? So the first number, it's how far apart the waves are. That is our wavelength. The second tells us how much time passes for the 10 crests. So that, to me, if you have 10 crests in 45 seconds, that looks an awful lot like a frequency to me because it's waves per second. That would be a frequency of 0.22 hertz, and we are looking for the velocity of the wave. So that is going to be frequency times lambda. And that is 5.3 meters per second. Number 6, a typical tidal wave tsunami can have a speed of 750 kilometers per hour and a wavelength of 320 meters. Find the frequency and the period of the wave. Again, these units are not very nice. I've got kilometers and meters, and I'm not going to do this to you on the test. I will try to give you some nicer units. So the first number that we have is the speed. And this is the wavelength, 320 meters. We have a problem in that the kilometers and the meters don't go together. So we have to change the 320 meters into kilometers to make this one work out correctly. We're looking for frequency and period, but first we'll find frequency because that's the equation that uses those variables. So we have 750 equal to frequency times 0.32. We'll divide both sides by 0.32. That gives us a frequency of 2,344 waves per, and then look at that. That's in hours. So this is actually waves per hour, which is a really odd unit. That's why I said I would not do this to you on the test. The period, so that's the answer to A. And for B, the period is just 1 over that number. 1 over 2,344 is a really tiny number because it's in hours, 0.00043 hours. If you multiplied by that by 60 to get minutes, or by 60 another time to get seconds, that would be fine with me. It actually is every 1.54 seconds. That's how many, that's how much time that is, because the 0.00043 hours doesn't really have a lot of meaning to us because we don't talk about hours that small. Number 7, a seismic P wave in an earthquake travels at 8,000 meters per second and has a wavelength of 2,000 meters. What is its frequency? We have velocity and we have wavelength. And we're looking for frequency. So we divide both sides, oops, one extra, by 2,004 hertz is the frequency. I can get my papers apart. It's a challenge. Oh, success. Okay, second page, number 8. The wavelength of a 343 hertz tone in air is 1 meter. Sound travels at 1,530 meters per second in seawater. What is the wavelength of this same tone in seawater? So this is a bit of an odd question. There's a lot of numbers being thrown at us here. The hertz is our frequency. And then we have a wavelength of 1 meter in air. Then they give us a speed for water. And they want to know the wavelength in water. So this wavelength is really throwing us off. If we're trying to find an equation, this is everything in an equation, but one of these is in air and this is in water. And we're looking for the wavelength in water. So we're just going to ignore this. That was just like a nice little juicy tidbit of information they threw in there to make things confusing. Our equation is the same one we've been doing. So we have the velocity and we have the frequency. And we're looking for wavelength. So that same tone in the water has a wavelength of 4.5 meters. So it was only a meter in the air, but it's 4.5 meters in the water. 8 seconds after shouting hello in a canyon, an echo returns to you. How far away are the canyon walls to you? As I mentioned at the top, this equation here is for echoes. So anytime you see an echo question, you want to think about just good old velocity equals distance over time. And there's one other trick we want to think about. If you are standing and shouting at a wall that is some distance away from you, and that sound gets reflected back towards you, then the time for the echo to go and come back actually happens over twice the distance. So if it's 8 seconds, that means it was a 4-second trip to the wall and a 4-second trip back. So the time we actually want to use is 8 divided by 2, which is 4 seconds. And then we need to know the velocity of sound in air, which is a number that I gave you at the top of the page, and that will help us find our distance. So V equals D over T. Now to solve this problem, it's a little bit weird. I multiply both sides by 4. That gets rid of that. And then D is going to be 343 times 4, which is 1,372. In number 10, we have a dolphin who's chasing a school of fish. He emits a sonar pulse that travels 2,500 meters per second. If he receives the echo of the sonar pulse in 0.8 seconds, so there's that word echo, how far away is the school of fish? So we have the time for our echo is 0.8 seconds. We want to half that because we only want the distance to the school of fish. We don't want the distance back again. So D is our question mark. our same equation, V equals D over T. We're going to multiply both sides by 0.4. And our distance is 1,000 meters. All right, the last three questions are pretty fast. Just a simple subtraction. At the top of the page, I gave you an equation for the beat frequency. You just take one frequency minus the other frequency. When they're very close in pitch, we just have a simple small number frequency of beats that we hear. That's that wobble sound that we hear that I just showed you in class. If a violin and a piano simultaneously sound notes with frequencies of 434 and 440, the beat frequency you would hear would just be the difference in those notes. I wrote it backwards, so let's squeeze that in. 440 minus 434 is a 6 hertz beat frequency. That's the answer. Number 12, a clarinet tuning her instrument to an A note, 440 hertz with an auto tuner. Here's a 4 hertz beat frequency. The two possible frequencies she would be playing at would either be +4, she could be at 444 hertz, or she could be 4 below, which would be 436 hertz. We don't know which one without some more information. And in part B down here, it says she tightens her reed to raise the pitch, and then she hears a 5 hertz beat frequency. So that means that she is farther away from 440. And if she raised her pitch here, she would have been closer to 440. So that means that the 444 hertz was the right answer. That's the frequency